Good morning. Welcome to the first lecture from unit number 4 on antenna basics. So as I have mentioned in my notes, from unit 4, the topic 1 is on antenna basics. In this topic, we are going to discuss definition of an antenna and the radiation mechanism of all the types of antennas. Irrespective of type of an antenna, the radiation mechanism is same. So an antenna is defined as usually a metallic device such as a rod or wire for radiating and receiving radio waves. The IEEE standard defines the term antenna as a metallic device which is a means or which is a medium for transmitting and receiving radio waves. So an antenna can transmit as well as receive radio waves. This is a general definition of an antenna. An antenna is also termed as an aerial, and it is connected to a source which can be a transmitter in case of transmission case, and it can be a receiver if it is receiving case. So let's have a look at a diagram which shows radiation mechanism of an antenna. You can see a source here which is consisting of a message signal modulating the carrier, or it can be a receiver also if the antenna is acting as a receiver antenna, and this source produces electromagnetic wave inside a transmission line. This transmission line we have studied in unit number 1, and the transmission line can be in the form of a coaxial cable or a simple 2-conductor transmission line or a waveguide, and these electromagnetic waves travel further up to a structure which is a transition structure called as an antenna. This transition structure converts the guided electromagnetic wave into free space waves. So that's the important point to decide by the antenna, is to how to convert a guided electromagnetic wave into a free space wave and vice versa. So let's have a look at the radiation mechanism of an antenna. Radiation in an antenna is based on a single principle irrespective of the type of antenna. So it can be any type of antenna, its radiation mechanism remains same. And in order to achieve this radiation, an antenna should experience an accelerated or decelerated charge, because we defined in case of an antenna that it is a metallic device. So there are charge carriers moving in it. So the charge carriers are either accelerating or decelerating. Thus, the current flowing through the metallic rod is time varying. As you can see here, I dot indicates a time changing current inside a length of metallic rod L, or it can also be considered as a charge moving with velocity V, which is time varying. So we can conclude that a time changing current can radiate, and it is also true that an accelerated charge can also radiate. So these are the basic mechanisms of basic topics in the mechanism of radiation of an antenna, but these definitions or these concepts do not tell us clearly how a guided electromagnetic wave gets converted into free space wave and vice versa. In order to understand this concept, let's take an example of a voltage source connected to an antenna through a transmission line. As you can see in my notes which I have shared, you can see the page numbers of the notes. The first topic, after page number 3, you directly see page number 8. And on page number 8, I have tried to give you an explanation of radiation mechanism with the help of a simple dipole. So you may be surprised to see whether I missed the pages in between from page number 4 to page number 7. But the fact is, I just wanted to make these notes simple, short, so that while reading these notes, you will not have an opinion that the very first topic in the antenna is so lengthy. So what I have made, I have eliminated all those pages. So in the next couple of minutes, I will try to explain you what exactly is the content on those pages. So all of you know that when a voltage source is applied to a metallic plate or a metallic conducting plate, such as this transmission line shown here, there will be always electric field, and this electric field will have electric lines of force associated with the field, which we can see here. Now these two different kind of structures shown inside a rectangular waveguide is for a simple reason that the applied voltage source is sinusoidal, and if this is indicating a positive cycle, then this portion is indicating a negative cycle. But in both the cases, you can see the field line is originating on positive charge and it is ending on a negative charge, and here only the position of field charges is changed. Here we have shown positive, field lines are originating on positive and they are ending on negative. As you can see, this portion is the transition portion in which the guided electromagnetic wave is getting converted into free space wave. So how this exactly happens? Once the electric field lines are generated inside the transmission line, these field lines are tangent to the point at which they are generated, and their strength is proportional to the electric field intensity. The electric field lines of force have tendency to act on free electrons. So there are free electrons. Of course, we are talking about a transmission line and metal. So the free electrons are in the atoms of metal, and when these free electrons experience the force, then they get displaced, they move, and their movement results into a current. And as you know, the current, so there is something called like this sequence, where first the free charges or charges which are detachable from atoms, they move, and this results into current, and the current results into a magnetic field. So the journey which started at electric field ends at magnetic field. So electric field accelerate the charges, the movement of the charges results into current, the current produces the magnetic field, and then associated to this magnetic field there exist lines, magnetic lines of force, which are tangent to the magnetic field. So now I think you can understand that in this entire process, from electromagnetic basics, the generation of electromagnetic wave has taken place, and this electromagnetic wave is traveling inside this transmission line. The electric field lines drawn between two conductors, they help us to display the charge distribution. So what we see here is basically the charge distribution, and since we have assumed that the field, applied electric field or voltage, is sinusoidal, therefore the electric field between the conductor is also expected as sinusoidal, with period equal to the period of applied sinusoidal source. This can be considered as a bunch of electrons or a bunch of charge carriers having electric field intensities, and these bunches of electric field intensities are traveling. These bunches indicates the creation of time-varying electric and magnetic fields between the conductor, and electromagnetic wave is formed which travels along the transmission line as shown in this figure. The electromagnetic wave enters the antenna, and associated with it there are electric charges and corresponding currents. So once the antenna radiates these bunches of field lines into free space, we can see here arrows pointing downward are available here at point P2 and arrows indicating upward are available at this point P0. If we connect these open ends of the electric field lines, we can see this as a free space wave. The free space wave is also periodic, but it is constant at point P0 and it moves outwardly with the speed of light, and it travels at a distance P1, which is usually lambda by 2 to the point P0, and another lambda by 2 distance from P2 to P1 in 1/2 of the period. Near the antenna, this field has velocity which is slightly faster than the speed of light, and then as it slowly approaches a distance of P2, its velocity decreases and reaches the speed of light. The question still remains is how the guided electromagnetic wave detaches from the antenna and it becomes a free space waves. This can be explained by taking an example of dropping a small stone in a calm body of water. If we assume that the surface of the water is calm and if we drop a small stone, disturbance is created in the water. It is initiated on the surface of the water, and this disturbance can be considered as a wave generated. This wave travels outwardly. If the disturbance is removed, the wave do not stop or destroy themselves, but continue their course of travel. The disturbance that we have considered in our example is the stone. If we are continuously generating this disturbance, the generation of waves continues. This is exactly what happens in this case, where the disturbance is generated by the applied source and the electromagnetic waves continue to generate and detach from the antenna. Thus, this explanation leads to the concept. I think this page number 8, you can see in my notes, where we conclude the principle of radiation by saying that the electric charges are required to excite the fields but are not needed to sustain them and may exist in their absence. Once the electromagnetic wave is generated, just like in the example of generating a disturbance on the surface of calm water body, the electromagnetic wave is generated and it sustains them and it exists even if the disturbance is stopped. Now let's study a mechanism by which these electric lines of forces are created, and they travel by taking a simple example of a dipole. Let me zoom on these images so that we can clearly see these pictures. So the first diagram indicating here a dipole antenna. There is a positive charge at which the field line is originated, and then there is a negative charge on which the field line ends. We can see the mechanism of detachment of electric field lines of force is explained with the help of this dipole antenna. So let us consider that dipole has two charged particles and they are opposite. The field line is originated on positive and it is ending on negative, and the separation, or you can say the length of this dipole, is L. So at time t equal to 0 here, you can zoom on this image slightly so that the details can be seen. So let's say at time instant t is equal to 0, we are assuming that the charges are separated with a maximum separation and they are undergoing acceleration v. This is a time varying velocity, and the acceleration is also maximum as they reverse their direction. This is shown in the first figure. At a certain instant t is equal to 1/8, you can see in the second figure, the current has started flowing. This is a simple harmonic current. As I mentioned earlier, there has to be acceleration and deceleration of charged particles along the conductor. The current starts flowing, which is a time varying current, and at the instant 1/8 t, the current I is 0. At 1 by 8 period later, after 1 by 8 t, the charges are moving towards each other as it is shown in this image. At 1/4 of time, the charge carriers have reached the midpoint. We can see here at t is equal to 1 by 4 at the midpoint, and the charge particles have crossed each other, and at that particular point there is detachment or disconnection of this first field line and a new field line which is exactly equal to the previous field line, but with the opposite sign is generated, and the charge particles have started their journey in the opposite direction. So as you can see here in the next figure, at time instant t is equal to 3 by 8 t, there is one wave detached, there is one field line detached from the dipole antenna, and the newer one started at positive terminal and it is ending on the negative terminal. So this process continues, and the radiation is seen finally in this form at t is equal to 1 by 2t. Okay, the distance between the wave front, this is called as wave front, you can see here wave front, the distance between the first wave point and the next wave point, successive wave point, is considered lambda by 2, and this wave front is deciding the generation, the speed with which the electric field lines are generating in the successive cycles. So to put a final word on the radiation mechanism of antennas, let's assume, as shown in this diagram, there is a positive charge, and on this positive charge there are field lines originated and they are ending either on the negative charge or they are ending into the infinity. So if we assume that this charge is moving with a constant velocity in z direction, it is surrounded by static electric field lines. When charge moves from one point to other point in free space, the field lines also follow the charge and they surround the charge. Due to the difference, because the charge particle is moving with higher velocity and the field lines are moving with a lower velocity, due to the difference between these velocities, the charge moves from one point to the other point early, and the field lines follow it, and they form a structure very similar to shown in this point. So let's say if this is a point A and the charge particle is moving at point B at a certain time interval, the charge particle will move first and the field lines will surround the later time. The disturbance is generated basically because of the differences in these velocities, and this disturbance itself is called as radiation. In the previous video, we defined antenna. We studied how radiation takes place with the example of diagram shown with the help of transmission line and antenna structure. So this was the transmission line and this was the antenna structure. We studied the radiation mechanism with the help of a simple dipole and the positive and negative charge lines, charge carriers and associated field lines. In the next lecture, we will discuss about patterns that an antenna produces when the electromagnetic wave guided inside a transmission line is transmitted by an antenna in the free space. Thank you.